Chemical Nomenclature, Part 2, Ionic Compounds, Turning Chemical Names into Formulas. In our last video, we took a look at this sheet and how we could use the periodic table to look up charges for some elements that were very predictable based on their atomic structure, and for other elements, and for polyatomic ions, we could look up their formulas in a piece of reference material like this ion reference sheet. Now, this is not an all-inclusive sheet. If you wanted an all-inclusive list, you'd have to look at a complete reference book like the CRC index or the Merck index, or you could Google the formula for ions if you knew their names as well. So if you haven't seen that video, that's Chemical Nomenclature Part 1, and you should watch that video if you have trouble finding ions on this sheet or if you're a little confused about that. Certainly if you haven't watched that before this video, you should watch that first. Ionic compounds are of course made of ions, and they're written with the positive ion first, negative ion second. For positive ions, if they're monatomic, we just use the element name to name those ions. So for example, Na1+ is sodium ion, Mg2+ is magnesium ion, Al3+ is aluminum ion, and so on. We just use the element name for those ions. If it's a positive polyatomic ion, there's really only one that you really have to keep your eye out for, and we put a star by it on this sheet to help you find it. It's the ammonium ion. Remember, hydronium ion is really only used in acid-base chemistry. For negative ions, if they're monatomic, we refer to the ion with the element name, but we change the suffix or the ending to IDE. So for example, N3- is nitride, P3- is phosphide, O2- is oxide, F1- is fluoride, S2- is sulfide, and so on. All of these negative monatomic ions would have IDE endings when they have those negative charges. Negative polyatomic ions would have an ite or an ate ending. So the ite and ate suffixes can be found mixed in here, and there's a little note to remind you about that. So for example, sulfite is SO3 2-, sulfate is SO4 2-, thiocyanate is SCN1-, thiosulfate is S2O3 2-. You can look up the formulas for negative polyatomic ions with ite and ate endings in here. And be aware that there are two exceptions that have IDE endings. They have asterisks by them. CN1- for cyanide, OH1- for hydroxide. A little bit odd that we have some IDE polyatomic ions, but they do exist. All right, so we're going to use the criss-cross and reduce method when we're turning a chemical name into a chemical formula. And remember, there are two steps for this. Now, it's really important that you know how to do criss-cross and reduce. Moving on in chemistry, we're going to use this very much. So if you don't understand this, it's going to be very confusing as we get to subsequent chapters. So the first thing we're going to do is write the ions for the chemical, and then the second thing we're going to do is criss-cross and reduce. Let's take a look for a compound, magnesium oxide. Half of the battle is finding the ions. So we're going to look on the periodic table first, and we can see magnesium, Mg, is in the 2+ column. Always cross-reference positive ions and look up here and see if it's got more than any other possibilities for charges. It'll be listed up here. We can see magnesium is not. So magnesium is always and only 2+. Notice there's no Roman numeral there. Oxide is going to be O for oxygen with a 2- charge. It's oxide. So what we're going to do is take this 2 and crisscross it down there, and take that 2 and crisscross it down there. Now when we have 2 and 2, they reduce, and we get 1 and 1. You'll notice we don't write a 1 and we don't write a 1 because we typically just put, we omit the ones from the formula. So if you don't see a number written down there, that would be an unwritten 1. Now, at the very minimum, you should write the ions, write the formula, and you can do some of that work in your head, but at first you might find it useful to actually write the arrows in and do the work that I'm showing here in red. So we would take the 2 from Mg2+ and put it down by the O, and take the 2 from the O2- and put it down by the Mg. We crisscross those numbers down to the bottom. Notice we drop the minus sign and we drop the plus sign. The idea here is we're always going to end up with neutral compounds. If the positive sign, charges and the negative charges are equal, we have a neutral compound, the charge is balanced, and that means all the electrons lost, creating the positive charge, balance out all the electrons gained, creating the negative charge, and since all the electrons are accounted for, we've satisfied the law of conservation of mass. So all compounds are going to be neutral. We don't include any charges when we write compound formulas. All right, back to this. We initially take this 2 and move it down, so we see it's down here. We take this 2 and we move it down, so we see it's down there. Now 2 and 2 can be reduced. The way we reduce a ratio like 2 and 2 is we divide the numbers in the ratio by the same value. So 2 divided by 2 turns out to be 1, and 2 divided by 2 turns out to be 1. We can divide both of those by the denominator 2, and we end up with 1 of each. Now, they don't have to be the exact same numbers. A 6-to-3 ratio can be divided by 3, so that 6 divided by 3 is 2, and 3 divided by 3 is 1. So 6-to-3 becomes 2-to-1. You can divide any ratios, or you can simplify any ratios, reduce them, as long as the numbers in the ratio are all divisible by the same whole number. Just real quick, some notes here. Remember, we need to use Roman numerals when the positive ion has more than one possible charge. Now, this doesn't ever happen with negative ions, but it does with positive ions. Let's take a look at an example here, cobalt. Now, we would look for the elements first on the periodic table, and we see that cobalt, CO, is in the part of the table where we can't predict its charge. So experimentally, it has been determined and written down here that cobalt could be 2+ or 3+. So let's list both of those. And let's see how we would refer to that. Remember that 2+ would tell us that we'd have to use Roman numeral 2. And if it's a 3+, we would use Roman numeral 3. So we call this the cobalt 2 ion. We call this one the cobalt 3 ion. And you should remember those Roman numerals. Again, you might want to check out the last video if you're confused about that. Now, there are some ions that don't have more than one possible charge. For example, if we're talking about zinc ion, and we look at zinc on the periodic table, and here see it's not predictable based on its location on the table. For example, like Mg is always 2+, we can't tell that with zinc. So based on experiment, we know that zinc is a 2+ ion, and there are no other possibilities for zinc. If it's not listed up here with more than one charge, like Pb could be 2+ or 4+, then it only has one possible charge. So if we don't see it listed here at all, or if we see it here listed with only one possible charge, then we don't use Roman numerals. So we would just call that the zinc 2+ ion. It's always important that you cross-reference, because sometimes you might find a charge on the periodic table for an element, like for example, Pb looks like when it's positive it would be 4+. But if you don't check up here, you might not know that, hey, Pb can also form a 2+ charge. Now, that happens sometimes. So always cross-reference for positive ions by looking here and looking here. Negative ions, we don't have to worry about it. We can find all of our monatomic negative ions right here. And of course, polyatomic ions that are negative, the ites and the eights for the large part are all ites and eights in here. We can find right in that spot. Another important point here is that you should use parentheses around polyatomic ions when you crisscross and put a subscript on the outside. Let's take a look at an example with Mg, magnesium ion, has 2+ charge, and OH is 1-. This is magnesium hydroxide. OH 1- is hydroxide. Mg is in the 2+ column. When we crisscross this, we take this 2 and we put it down here, and we take this 1 and we put it down there. We don't write the 1 in the formula, and the 2 has to go outside of parentheses. So the way that we interpret that is that there's 1 Mg and 2 OHs. Now that actually means there's 2 times 1 or 2 O's and 2 times 1 or 2 H's. But what's important is that if we have 2 OHs, that's 2 minuses, and 1 Mg2+, it's balanced out and it's neutral. If we write it this way, it's incorrect. Notice there are no parentheses here. There's not a left or right parenthesis around the OH. So the way that it's written here would indicate 1 Mg, 1 O, and 2 H's. That's wrong. You got to put parentheses on that. So even if it's a simple polyatomic ion like OH, if you want to crisscross a number outside of it, you have to use parentheses. Now the way that we would refer to this if we were speaking about it is we'd say magnesium, we give a little pause, and then OH taken twice. So Mg, OH taken twice. When you see that it's taken so many times, it means it's in parentheses. Here's another example with parentheses. Here we have sodium combining with sulfate. Sodium is in the 1 plus column, Na1 plus. And if you look up here, you see it's not written with any other charges, so there's no need for a Roman numeral. And then sulfate is SO4 2 minus. So this compound would be called sodium sulfate. Now when we crisscross it, we put the 1 there, and we put the 2 there. Right? 1 goes there, 2 goes there. Now, SO4 taken once doesn't really have to be written that way. We don't need to write that 1. And if we don't need the 1 written there, we don't need the parentheses either. So we just write it as Na2SO4. Now you might be tempted to start reducing the 2 and the 4, but be careful, you can't do that. The only numbers that can be reduced are the numbers that we're crisscrossing. So the only candidates for being reduced are the 1 and the 2, and of course 1 and 2 don't reduce. Numbers that are already on the bottom, the subscript numbers in the formula for a polyatomic ion, like the 4 in SO4 2 minus or the 3 in SO3 2 minus, numbers like that can never be reduced. They have to be in there. So you're going to start to recognize ion formulas just because we will be using these a lot. So you'll be able to recognize that this compound, which is always made of 2 parts, a positive part and a negative part, is made of sodium and sulfate. And when you notice that sodium doesn't have any other possible charges on there, you can see why there's no Roman numeral involved in the name of that. That's just called sodium sulfate. Now remember that the Roman numerals indicate the ion charge, not what the subscript is. So, for example, platinum, which could be 2 plus or 4 plus. If we see platinum on the periodic table, we can see it's right here. We can't predict its charge because it's in the middle part of the table there. So we look up here at the experimental results and we see that platinum could be listed, or is listed, as a 2 plus or a 4 plus. So if we say platinum 2, we're referring to the 2 plus version of platinum. When we crisscross platinum 2 with the oxide ion, which is O2 minus, the 2's crisscross and then they reduce. So we're not using that 4 there at all. This 2 goes here and that 2 goes there. Again, Roman numeral 2 for 2 plus. 2 and 2 reduce because they're both divisible by 2, and the formula for this compound is PTO, 1 platinum, 1 oxide, and platinum 2 oxide. Remember that if we don't write the 1s, we just make the assumption that any unwritten numbers are 1s. If we see platinum 4 oxide where we're using the 4 plus, notice 2 and 4 crisscross, and initially we get that formula, but then they're both divisible by 2, so it reduces down to PT1O2, right? 2 divided by 2 is 1, 4 divided by 2 is 2. So PTO is platinum 2 oxide, PTO2 is platinum 4 oxide. It can get a little confusing. It's always important that you write down the ion formulas first. Don't just assume that you can remember the ions in your head and do all that crisscross and reducing in your head without having any ions to look at. Always write the ions down. Here's an example of where it can really be a little tricky. Let's consider gold 3 hypobromite. Gold 3, if we find gold on the periodic table, we see it's right here. Not a predictable charge because we don't have any charges written above like over there. So we look at the experimental results and we see gold could be 1 plus or 3 plus. Gold is AU. So when it says gold 3, we're talking about gold 3 plus. Now hypobromite is an example of a halogen oxide. We went over this in the last video, so you might want to review that. Halogen oxides are when fluorine, chlorine, bromine, or iodine, these are the non-radioactive halogens from group 17, combined with oxygen to form negative ions. And they all follow this same basic pattern. And here we've put chlorine into that pattern so we can see the different ion formulas and different names for those ions. So if hypochlorite is ClO1 minus, and bromine works the same way, then BrO1 minus would be hypobromite. So we take Au3 plus and BrO1 minus and crisscross that, and the 1 goes there, and the 3 goes there, and we get AU1 BRO taken 3 times. Notice we say it's taken 3 times because that part's in parentheses. AU, pause, BRO, taken 3 times. All right, so contrast that with gold 1 bromate. Here we see gold 1, so that's AU with the 1 plus version, and then bromate. Now, if chlorate is ClO3 1 minus, remember these are halogen oxides, then all 4 of these halogens work the same way, combining with oxygen. BRO3 1 minus would be bromate. Again, that works for fluorine, chlorine, bromine, and iodine, the 4 common halogens here. So BRO3 1 minus is crisscrossing with AU1 plus. We put the 1 there and the 1 there, always positive first, negative second, right? And we don't write those ones, so this is our formula. If you wanted to write the parentheses and the 1s, it would look something like that. AU1, BRO3, in parentheses, taken once. So notice this is gold 3 hypobromite, and this is gold 1 bromate. It can be very confusing, and that's why it's important to always write the ions out first.